microscopy. We talked about optical, then transmission electron microscope. We looked at various aspects of transmission electron microscope, particularly the microscopy part of it and the diffraction part of it. Today we will discuss about the scanning electron microscope, which we started in the last class. SEM is what it is usually called in short, which is a scanning electron microscope. And we mentioned yesterday that scanning electron microscope is a microscope where, as the name suggests, that we use electrons as a source of imaging the microstructure of a sample. And the only difference is this is scanning microscope, whereas the previous one that we talked of is a transmission electron microscope. So the difference comes in the TEM you have electron beam going through the sample and then coming out and then getting focused onto a screen where you actually observe the image of the sample. Whereas this is what it is, TEM. In a scanning electron microscope you have the electron beam reflected from a surface and you are seeing the surface features of the sample, and this is what we call it as a scanning electron microscope. So as a result, there are certain limitations which are there in TEM which are not there in the SEM. So for example, here you need the sample to be very thin, we said, because the electron beam has to go through it, and here you don't have that problem because the electron beam is not passing through the sample and it is getting scattered from the surface, so you don't need to bother much about what is the thickness of your sample. In principle, as much as the size of the sample which a chamber can accommodate, one can actually use. When I say a chamber that can accommodate, basically what we mean is, because we are talking about electrons, in both these techniques, what you need is a high vacuum so that these electrons are not scattered away by the gas molecules, and as a result you need to have a chamber in which these electrons are generated by, again, the same two techniques that we talked earlier, the first one being a thermionic emission, second one being a field emission. So either use a thermionic emission or a field emission. So you can have one of these two guns in your SEM, similar to what you have it in a TEM, whether it is a tungsten filament which is thermionically emits electrons by heating the filament, or you apply a field which will emit electrons. So both these can be used, and usually we have seen in the previous classes also a field emission gun, the so-called FEG. FEG gun gives you a much better brightness of the beam, and also it gives you a longer life, and not only that, it gives you a better resolution. So even the resolution can be better with field emission. So many a times people nowadays are going for the field emission gun instead of going for a thermionic emission gun. But in that particular case, obviously you need to have a high vacuum so that you can see that these electrons are not scattered away. But the field has grown to such an extent nowadays that you also have SEMs which are called environmental SEM. People call it as ESEM. ESEM is a microscope where people do not use very high vacuum. In fact, they even use a pressurized chamber so that you can put anything. The problem with a high vacuum is that you have to have a sample which is highly, non-contaminating sample. For example, if I have a sample which is when an electron falls on it and something from the sample gets evaporated, let's say biological species for example, or some polymers for example, when an electron beam with a certain intensity and certain energy falls on the surface, obviously there will be something which is emitted out because of the low vapor boiling points or high vapor pressures of some of the ingredients in these materials, and as a result there is a possibility of something being evaporated, and that influences the vacuum that you have already created inside the sample. So as a result, these particular TEM and SEM, which are usually the conventional TEM and conventional SEM, are not basically meant for all kinds of samples. Particularly if you have biological samples. For example, I want to simply take a leaf and put it into a SEM and see the surface topography of the leaf and also microstructural features of the leaf. That is very difficult in this kind of high vacuum TEMs or high vacuum SEMs, basically because they have a tendency at some energy levels of the order of, for example, in SEM we use around 30 kV electron beam. In a TEM, starting from anywhere from 100 kV to about 300 kV, these are the standard TEMs. So at these energies, you have a lot of energy contained in this particular electron beam, which when it falls on the sample, it can damage the sample. Not only damage the sample, it can cause some evaporation of some of the ingredients of the sample. That can influence the vacuum. As a result, people now want to use microscopes where you don't have a high vacuum. People even call it as a low vacuum microscopes, or people even call go to the extent of completely avoiding any vacuum setup and even possibly pressurizing the chamber with a little bit of a positive pressure using an argon gas or something like that. But the question that arises in our mind is, then how is that these electrons are able to fall on the sample and give you an image? And that's where what they do is they bring down the distance between the electron gun and the sample to be very small, so that the volume that it is contained between the sample and the electron gun is so small that the electrons actually do not get disturbed when they are falling on the sample and are being collected by the detector. So these are the certain new advancements that have taken place in microscopes, particularly electron microscopes, that now you have these ESEMs available and quite a number of people are going into buying these ESEMs where you will be able to get a lot of information. Of course, at the same time, ESEM also has a problem in terms of the resolution because of this whatever little scattering that takes place between the atmosphere that is contained between the detector, between the source of the electrons and my sample. This particular region where the atmosphere is there, as a result, the resolutions that we achieve are to some extent influenced. So people, whoever are concerned with a very high resolutions, they still use a high vacuum microscope. And wherever you can compromise with the resolution a little bit, but are interested to see samples which have a tendency to, create certain, what is called evaporation of certain ingredients, you still go for a ECM. So this is one of the considerations that we need to remember, and one of the constraints of the ECM that one has to understand. So we will mostly concentrate on the high vacuum microscope, which is the most popular one, and try to look at what are the features of this scanning electron microscope and what it can do, which possibly the TEM cannot do. Most important thing that you can see here is in a SEM, mostly because we are using the electron beam to see the surface of the sample, we confine ourselves to what are the surface features that we can usually observe. And when we say surface features, one of the most important thing that comes to our mind is not only just the microstructure. For example, if you have an alloy of an aluminum silicon alloy. Aluminum silicon alloy, we all know that in an aluminum silicon alloy, you have depending on whether it is a hypoeutectic or a hypereutectic, let's consider aluminum silicon alloy, which if you can look at the phase diagram, which is something of this sort, with silicon on one side and the aluminum. So this is aluminum on one side, silicon on the other side. And if you are choosing a hypoeutectic, we were talking about this microstructure of features that we observe in a scanning electron microscope. So the similar features that we usually see even in an optical microscope can be seen even in a scanning electron microscope, excepting that you can see them with a better resolution. As we said earlier, the optical microscope has a limitation in terms of the resolution, whereas an electron microscope, because the lambda being very small, you can achieve the same microstructures, be able to see the same microstructure with a much better resolution. And if you are looking at regions like an alloy of this sort, let's say 7% silicon, because this is usually about 11.7%. That's where the eutectic is. And this alloy is supposed to contain, if you look at the microstructure, it should have dendrites of aluminum, and the interdentic regions, if these interdentic regions, you have basically silicon needles and alpha matrix. So silicon will be in the form of needles and alpha is in the form of a matrix. So you have this alpha at two places, one in the interdentic regions and one in the matrix, which is a part of the eutectic mixture. So you have proeutectic alpha plus eutectic mixture, and that eutectic mixture has alpha plus silicon needles. This is what is a microstructure. This microstructure you should be able to even see in an optical microscope, but one advantage that you can achieve in this scanning electron microscope is, because it has an excellent depth of field, you will be able to see the three-dimensional information about these particular needles. Are they really needles? Are they plates? Is an information that you can see by deep etching the surface. And if you deep etch the surface and then look at the surface, because it can show you the three-dimensional, the depth information, you can be able to see the actual, for example, morphology of silicon particles. Not only that, you can also see in different other microstructures. For example, if you are looking at what is called a gray cast iron. Gray cast iron, what we are supposed to have, that the graphite flakes. So are they really flakes, or what is the actual shape of these flakes is something that you can see by using this kind of a microscope. So one of the major advantages in terms of the microstructure is that you not only can see the final details with a better resolution, but also be able to see the shapes of these second phases. Particularly when you have an alloy with second phase, you will be able to see the shapes of these second phases very clearly and get to an idea of the correct shape of the second phase, which is not possible with a normal optical microscope. So that is one advantage of this particular scanning electron microscope, for which it has become very, very popular. The second thing that you can do with this microscope is what is called, again coming from the depth of field in this microscope from the surface, that you can use this microscope to understand the surface topography. Surface topography, particularly in an optical microscope, we actually polish the sample thoroughly to be able to see the image. The reason is, in an optical microscopy, the image formation happens because of the depth differences. For example, if you have a flat surface in which there are some grooves like this formed by, let's say, a grain boundary, and it is that groove is what you are seeing it as a black region when the light that falls on it gets reflected out, but not into the objective. You are able to see this as a black region, whereas this region looks like a white region in an optical microscope. Whereas in case of a scanning electron microscope, you would like to see these differences based on the electrons that are being scattered away from the surface, and looking at the number of electrons that are being collected back by the detector, and that gives you an information about, depending on the intensity of the electrons that are coming back, you will be able to see a kind of a contrast which is different for different regions depending on the depth. For example, if you have a surface which is having this kind of topology, whenever an electron beam falls onto this and then gets reflected back, because it is traveling a lot of distance, and in this region it can even get scattered away by the electrons present inside the sample. So as a result, this particular region, the electrons are lost before they actually reach. So if you are sending the electron beam with certain energy, with certain intensity, this intensity is lost by the interaction of this electron beam with this, and as a result you lose some of the intensity of the electron beam, and finally the electron beam that is scattering away and that is reaching your detector will have a lower intensity. So as a result, this particular region looks dark. So that's why whenever there is a pit inside your sample, you will see it as a dark region. Wherever there is a projection inside your sample, that looks like a bright region. So this is how you will be able to see the differences in terms of the contrast coming because of the differences in the intensity of the electrons that are reaching back the detector. And this is what we call it as a secondary electron image. The secondary electrons are the electrons which are coming back after being interacting with the sample, after getting scattered by the electrons of the sample, and whatever is reaching back, whatever is scattered backwards is what you are collecting. And this giving you an image of the surface topography. We can use this particular image to basically look at variety of surface features. For example, if a sample has undergone a fracture, yesterday we started talking about it, if it has undergone a fracture, depending on the nature of the fracture, the surface topography is going to be different. So these differences can be easily identified by using this secondary electron image, and from that we will be able to find out what kind of a fracture the material has undergone, whether it is an intergranular fracture or transgranular fracture. For example, if it is an intergranular fracture, the fracture usually occurs along the grain boundaries. If this is a grain structure of your sample, by any chance, if the grain boundary is very brittle, it could be because of a brittle compound present at the grain boundary. There are different types of microstructures where we see this kind of situation. For example, I can give you at least two examples. One is an aluminum copper alloy, for example. If you take an aluminum copper alloy, remember the aluminum copper phase diagram, for example, percentage copper increasing in this direction, and look at this phase diagram where if I choose an alloy of this type, let's say about 4% copper, the standard duraluminum kind of a composition, and this composition being around 5.8%. So if I choose this alloy, cast this alloy from its liquid state, what you see is that during the solidification, the liquid actually becomes a single phase alpha. This is like an isomorphous type of solidification. So once this alpha comes, as you further cool it in the mold, because this liquid has been poured into a mold, let us say, nucleation has taken place, and there is a growth that is happening, columnar growth, let us say, and once you have this alpha completely formed, no liquid is left out, this alpha, as you start cooling it to room temperature, you see that this alpha does not remain as single phase alpha when you are going towards the room temperature. The reason is this particular alloy under equilibrium conditions is supposed to have alpha plus theta at room temperature. So as a result, this alpha cannot remain as single phase alpha at room temperature, and the moment you cross this, which is called the solvus line, and the moment you cross the solvus line, you will see that the theta being precipitated out. The reason is, once you come to a temperature like this, the amount of copper inside alpha is this, whereas the solvus line tells you that the maximum solubility of copper in alpha at this temperature is this. So the amount of copper in my alloy is more than the maximum solubility of copper in the alpha at that temperature. So because of this difference, the excess copper precipitates out, and it precipitates out as theta, because in this phase diagram what you have here is a theta phase. So as a result, theta precipitates out. And where does this theta precipitate? It precipitates at the grain boundary. And if you give, if as you slowly cool and more theta forms, and this theta starts forming everywhere at these grain boundaries, nucleates at these grain boundaries, and finally spreads out around these grain boundaries and forms like a thin layer at this grain boundary. Now you will see that this is a microstructure at room temperature. If I look at this microstructure, I will have simply alpha plus theta at the grain boundary. This is like a thin sheet at the grain boundaries. You will have this theta decorating, and such an alloy when you look at it and look at its mechanical properties, if I subject this alloy to a tension, let's say I pull it, then you see whenever there is a crack that is nucleated inside the material, crack gets initiated, the crack can easily, instead of crack propagating through the grain, it will easily propagate through the grain boundary, because the crack, you have a brittle phase at the grain boundary, and a brittle phase is a material where the resistance for crack propagation is very small, so you can see the crack propagation very easily. And hence you will see that the material just separates out at the grain boundaries as if you have the whole material being pulled out at the grain boundary. So we were talking about the intergranular fracture, which can happen because of the presence of a brittle material at the grain boundary. For example, aluminum copper alloy, we just now said that if you have an aluminum copper alloy which is solidified from high temperature to a solid state at room temperature, what you are supposed to have at this temperature is an aluminum alloy containing alpha plus theta, and the theta phase, because of the nature of the precipitation, it precipitates at the alpha grain boundaries which are formed in this alloy by the time this alloy reaches this temperature. At this temperature, your alloy mostly has just alpha everywhere, because it's supposed to be a single phase alpha. And this alpha, as it starts cooling, will have the theta at the grain boundaries, and the theta decorates the whole grain boundaries as a thin layer, and because of that, when you subject this material to a tension, whenever there is a crack that is nucleated, instead of the crack trying to propagate through the grain, it prefers to propagate through the grain boundaries, because the grain boundaries have a brittle region where the crack can easily propagate. As you all know, brittle materials are those where the resistance offered for crack propagation is very small, like a glass that we see in the window glasses, where you can easily break such a glass, or a ceramic, let's say coffee cup or something like that, where the moment a crack is initiated, it can propagate very fast. And similarly here, you will see that the crack propagation happens along the grain boundaries, and when I look at such a fractured surface, you will be able to see the grain boundary separation very clearly inside the material. So, but this can be basically controlled or to some extent minimized by not having the theta at the grain boundary. And in order to not have a theta at the grain boundaries, people do what is called edge hardening, where they take this alloy containing this theta at the grain boundaries, heat it back to this temperature, where all the theta dissolves back and you get a microstructure something like this once again, quench it from there, so that you don't allow the theta to precipitate during this quenching, and so that this alpha remains as alpha at room temperature. But now this alpha is a supersaturated alpha, because at this temperature the alpha is not supposed to contain this much of copper. Let us say this is 4% copper. You are not supposed to have this much of copper, because the solubility of copper in aluminum at this temperature is only this much, which is usually less than about 0.5% at room temperature. So such a alloy containing excess alpha, if you allow it on its own, it will precipitate out this excess alpha. And either you can do it at room temperature or slightly heat it to a higher temperature, like say about 150 degrees or 200 degrees, and we can precipitate out this excess copper. And this process is either called natural aging when it is done at room temperature, or artificial aging when it is done at higher temperature. And in both these processes, now you see this precipitate that is coming out, the excess copper that is coming out will not come at the grain boundaries anymore. The reason is, if you want the copper to be precipitated as the Al to Cu at the grain boundaries, you need the copper atoms from everywhere in the grain to travel up to the grain boundary and then precipitate out. And because we are doing it at low temperature, the diffusion rates are very low at low temperatures. So copper does not have sufficient thermal activation available for the atoms to move up to the grain boundary. So as a result, it prefers to precipitate within the grain. And when it is precipitating within the grain, obviously the theta cannot precipitate, because theta has a structure which is significantly different from that of the matrix, and such a precipitate, if it has to nucleate within the grain, it has difficulty, because this is a incoherent precipitate, because the structural difference between the matrix and the precipitate being significantly different, such a precipitate cannot nucleate inside. So the system searches for any alternatives, and that's where it starts precipitating what are called GP zones, which have exactly similar crystal structure as that of alpha, and which is BCC, which is FCC. So the matrix is FCC, and the zones which we call them as GP zones, linear crystal zones, also are FCC in nature because they are mostly copper clusters. And such copper clusters, more or less like a pure copper clusters, they precipitate out inside the grain from such a microstructure. If this is the alpha microstructure, they simply precipitate inside the grain everywhere, wherever there are certain heterogeneous sites. Still there is a possibility of nucleating on the heterogeneous sites, but because these are coherent precipitates, they do not need to have heterogeneous nucleating sites, and they can nucleate on certain crystallographic planes of an alpha, and you can have such a microstructure with all the precipitates contained inside the grains, and there is no brittle precipitate at the grain boundary. And such an alloy, when it is subjected to a fracture, you will not see an intergranular fracture, and in such a material the fracture propagates through the grain, and we call this as a transgranular fracture. And whenever the fracture is propagating through the grain, you will never be able to see these grain boundaries distinctly in the fractured surface, and that is how, by looking at the fractured surface, we will be able to say whether this was an intergranular fracture or a transgranular fracture, and whether you had a brittle phases at the grain boundaries or not is something we can identify very easily by simply looking at the fracture surface. There is also another similar situation that we come across in steels. For example, if you are dealing with a steel which is, let's say, hypereutectoid steel. Again, if I look at if you look at the hypereutectoid steel, for example, a steel with about 1.2% carbon or so, and you know this is gamma, this is alpha, and you have cementite on this side, and this region is gamma plus cementite. So if you take an alloy, heat it to a temperature like this, and then cool it, what you end up in is, at this temperature, your alloy is completely gamma, and as I start cooling from this temperature, the moment I reach this temperature, again you will have a similar situation. For example, if I come to this temperature, here at this temperature, the carbon solubility in gamma is only this much, whereas my alloy has this much of carbon, which is in excess of the solubility of carbon in gamma. As a result, this excess carbon will precipitate out as cementite, and that cementite precipitates out at the grain boundaries again. So like the previous microstructure that we have seen, you will have a cementite precipitating out at the grain boundaries like a thin layer. Again, cementite being a brittle phase, you will see you have a brittle phase nucleated at the grain boundaries and growing it. And ultimately, when you come to temperature which is a room temperature, here the remaining gamma gets undergoes a eutectoid transformation, and you will see a microstructure where you have eutectoid colonies, which is perlite colonies inside, and inside the perlite colony you have alternate layers of, let's say, alpha plus cementite, which is what we call it as a lamellar structure, and you have such a lamellar structure formed here, and similarly in other regions. So these are all perlite, whereas what you see clearly is there is a cementite at the grain boundaries, continuous cementite, what we call it as a network of cementite, and this is called a continuous network of cementite. And you will not see this in the hypoeutectoid steels, because in a hypoeutectoid steel, what precipitates from gamma is only a ferrite, which is a soft material. So we all know that ferrite is softer, whereas cementite, being a compound, is a very hard phase, and it's a brittle phase. And if you have such a brittle phase at the grain boundaries, the material will again fracture in an intergranular manner. So that's why all high carbon steels will fracture in an intergranular manner unless you do something with this steel. And what do we do with this steel? So, like what we have done in case of aluminum copper alloy, where we try to do precipitation hardening. Here we do not do such a process, but what we do here is there are two things one can do here. One is we can cool this alloy faster from high temperature, what we usually refer to it as normalizing. When you do normalizing of this alloy, cool it in air rather than cooling it in a furnace, what happens is cementite precipitates in this temperature domain, which is what we call it as intercritical domain, which is between ACM and A1. This is called A1 temperature, this is called ACM temperature. And this particular domain is when the cementite is nucleating and growing. If you cool it faster, the time that you are allowing for the cementite to precipitate in this domain is going to be smaller. As a result, cementite will not have a tendency to form a continuous network, and cementite will nucleate at the grain boundaries, no doubt about it, but that cementite will simply get confined to some discontinuous particles at the grain boundaries. So it will nucleate at various places, but it will not have time to grow along the grain boundary continuously, and as a result you will see that the continuous network is now broken into what is called a discontinuous network. This is one aspect. Second aspect is that when you are cooling it faster, because the time available is smaller, whatever is the total cementite that is supposed to come out according to the phase diagram. For example, if I take this 1.2% carbon steel, come to just above the eutectoid. Just above the eutectoid, if you calculate what is the amount of pro-eutectoid cementite, you will see that the pro-eutectoid cementite is nothing but 1.2 minus 0.8 divided by 6.67 minus 0.8. This is the actual amount of pro-eutectoid cementite. And this is, if I take it as 0.4 by 5.87. So this is approximately, if I take it around, let's say it is 6, if I take it as 6, so it's about 6%, roughly around 6.5% or so. So 6 to 7% is what cementite is you are supposed to get under equilibrium conditions. That is what the phase diagram tells us. But because I am cooling it rapidly, as a result, the time available being smaller, the total amount of this 7% does not come out. Only a fraction of this 7% or 6% comes out. As a result, the amount of cementite that can form at the grain boundary is smaller than what it can form during annealing. So that is another advantage for us, because all the cementite is not coming out for it to form a continuous network. So you will have less amount of cementite coming out because of the faster cooling, and also because the time available being smaller, it does not grow also along the grain boundaries. So finally what we see is a discontinuous network. And once you have a discontinuous network, if a crack is, let's say, trying to propagate along the grain boundary, the moment it comes across this region where there is no cementite, it cannot propagate further. So because this region is not as brittle as this region, so as a result, that particular region offers certain resistance for the crack propagation, and hence you will be able to see some the crack blunting starts happening in these kind of regions, and then you will see the material will not be as brittle as you otherwise would have expected, and that gives you a better mechanical properties in terms of the ductility in the material. So that's why normalized microstructures, particularly high carbon steels, are not as brittle as an annealed microstructure in case of high carbon steel. Usually you expect that annealing should make a material soft, whereas in case of high carbon steels, actually it is the reverse, that an annealing will make the alloy very brittle. If you do normalizing, it will give you some ductility. So this is one way to do this. The second way to do it is, after the alloy has been cooled in an annealed, let us say, and with a continuous network of cementite at the grain boundary, you can heat it back. For example, you wanted to do normalizing, by mistake you have not done normalizing, the alloy has already is having the cementite continuous network at the grain boundary. What do I do now? Can I solve the problem? Can we do some kind of a salvaging? That is where you can heat it back to a temperature which is below the eutectoid, or you can heat it to a temperature above the eutectoid, depending on the type of alloy. For example, if you heat it back to this temperature, what you see is that either this temperature or this temperature, depending on the availability of furnace with you. In principle, the higher the temperature, the better, because diffusions are much high, diffusion rates are higher at higher temperature. What you see is that this cementite, because it is like a continuous network, it has a large surface energy. Okay, so if you, every surface has certain surface energy. Because of the large surface area, A into gamma is the overall surface energy. And if you allow sufficient time, what happens is this particular cementite, which is present at the grain boundaries, can actually globularize, become like spherical particles. So this cementite which is there slowly starts becoming spherical particles at the grain boundaries. And by doing that, it reduces its overall surface area to volume ratio, because we all know that for sphere, the surface area to volume ratio is the smallest. And so instead of being like a sheet, it gets converted into spherical particles, provided you give sufficient time at a temperature where the diffusion of atoms is easier, and finally it reduces its overall energy. So this is one of the way by which we can convert a continuous network of cementite into globular particles, and this is what we call it as periodization. So this is another technique. You can either do normalizing, where you get a discontinuous network of cementite, or if you have already obtained a continuous network of cementite and you have found that the material is brittle, if you want to solve the problem, you can actually heat it back to a temperature something like this, where you can allow the cementite to convert into spheroidal particles. And if you continue to do this for a longer period, then you will see not only that the cementite which is there at the grain boundaries, which is a proetectoid cementite, becomes spheroids, but also the cementite inside the perlite, because inside the perlite also cementite is lamellar. This is the cementite lamellae. So this is also like a sheets of cementite, and these sheets of cementite also have a high surface area, and as a result high surface energy, and that particular cementite also can get converted, and hence you may end up ultimately into a structure where you will have completely spherical particles of cementite everywhere. So you will have a ferrite matrix and cementite particles in the matrix, and such a microstructure is what we call it as a completely spheroidized microstructure, where not only the grain boundary particles of cementite which are converted, but also the cementite inside the perlite also gets converted, and hence you will have a structure which is completely ferrite with cementite spherical particles, and you can achieve very high ductility in such a material. But ultimately what is important is, in a high carbon steel, the reason why I want to use a high carbon steel is to have high hardness. Otherwise I would have been satisfied with a low carbon steel. So because high carbon steel, the intention is to have basically a very high hardness. So people do not go for a complete spheroidization, because when you go for a complete spheroidization, the hardness comes down significantly, because it is these lamellae that we have will give you a high strength in the material, and also the cementite network at the grain boundaries, whether it is discontinuous or continuous. So if you convert that to completely ferrite matrix with the cementite particles, your strength comes down. Of course, at the same time your ductility significantly goes up, but one has to have an idea of what, for which kind of an application one would like to use this kind of a microstructure. So people usually try to have a spheroidization of this grain boundary cementite and control the spheroidization of the complete perlite. So this is one way one can possibly achieve higher strength and higher ductility, and in such a material, the material will not undergo any more intergranular fracture, but it will undergo a transgranular fracture, because there is no brittle network at the grain boundary. I also have possibly mentioned in the last class, we can also see such intergranular fractures in other cases. For example, one such case that we come across usually is in stainless steels, a concept that we usually call it as sensitization, where if you have a stainless steel, let's say an 18-8 stainless steel, 18% chromium, 8% nickel, stainless steel, which is an austenitic stainless steel, which is standard steel that is used for a lot of corrosion resistance applications. But the problem here is we know that corrosion resistance usually is seen in alloys when the chromium content, percentage chromium, is greater than 12. And if you want to maintain that percentage chromium as greater than 12, and which is what you see here, 18% chromium is added in order to achieve that stainless property. But this chromium has a tendency to react with carbon if there is carbon inside your material and form carbides such as Cr23C6. And as a result, usually stainless steels are maintained with a very low carbon content so that the chromium is not lost by combining with carbon and to give you chromium carbide. In case your steel has some carbon in it, what happens is this chromium will react with the carbon, and this reaction usually happens at the grain boundaries more easily. Because at the grain boundaries the diffusivities are higher, because grain boundaries are more open structures, so the diffusion of atoms can easily happen. So this Cr23C6 precipitates at the grain boundaries by the reaction of chromium with carbon. We are not more concerned with the precipitation of Cr23C6, but more concerned about the loss of chromium because of this reaction. So the moment chromium is removed out of the austenite and then gets reacted with the carbon and forms Cr23C6, the chromium content of austenite comes down. And what is important is the amount. It is not the overall chromium content of the alloy that is important for us. If you want to have high corrosion resistance, the chromium dissolved in the austenite, dissolved in the iron, should be greater than this. And the moment the chromium content of the austenite comes down below this value, suddenly you will see the alloy starts getting corroded at these grain boundaries, because it is these regions where the chromium content has come down. So as a result, you will see the material gets corroded at this surface, at this grain boundary, with some corrosion products, which are basically some kind of hydroxides or oxides that form at this particular grain boundary. And once you have such brittle corrosion products which are formed at these grain boundaries, the material becomes brittle at the grain boundaries, and again similar to what we have discussed in an aluminum copper alloy or in a high carbon steel, you will see a similar situation that the material fractures at the grain boundaries. In fact, people have seen cases where the whole alloy, the stainless steel, becomes like a powder because it just gets separated at the grain boundaries because of these corrosion products that form at the grain boundaries, and the material, a piece of stainless steel like this can simply just become a powder because each grain gets separated out, and that can happen, and that is what we usually call it as sensitization. Again, that kind of a fracture, which is mostly an intergranular fracture, can easily be seen by using a scanning electron microscope. So you can see that there are different microstructures where fractures can be mostly intergranular, and such intergranular fractures can be easily detected, and from that you can make out whether a sensitization has happened in a stainless steel or not by looking at the nature of the fracture, and then correct it out. In case you have seen that there is a sensitization in your alloy, that means we have an alloy with a higher carbon, so the best thing is somehow to reduce the carbon content so that you have the alloy with a lower carbon content. So we have now special steels which are called 304L. Usually 304 is or 316 are two popular austenitic stainless steels that we use, and they add a term L there just to give you an indication that is extra low carbon steels. So in these alloys the carbon content is maintained something like about 0.03% or even below that, so that you have an alloy with extra low carbon. So with this we will stop for a while and then continue in the next class on the other aspects of the fracture that we can observe using SEM.